I'm gonna go to explain you the question on the topic gases and kinetic energy. So this question has 3 different bits that I'm gonna go to explain you, and hopefully you're gonna get how to do this. Okay, so coming to the first question. A sample of 255 grams neon gas occupied 3 decimeters cubed at 122 kelvins. Using the ideal gas law, calculate the pressure of the gas. So the equation for the ideal gas is equal PV is equal nRT. So as we need to calculate the pressure is going to be equal to nRT divided by V. So as we know from the question, the mass of the neon gas is equal to 155 grams. The molar mass from the periodic table is equal to 20.179 grams per mole. So as we know, to calculate the moles, we need mole mass divided by molar mass. That is equal to 255 grams divided by 20.175 grams per mole. And it's gonna be, and the moles gonna be 12.6369 moles. So as we got on the question, the volume is equal to 3 decimeters cubed, and I converted it into meters cubed, 3 multiplied by 10 in minus 3 meters cubed. And the temperature is 122 kelvins. So everything that we have now, we're gonna just plug it into our equation, and we're gonna calculate the pressure. So the equation, we plugged everything in, and we got a long number that is gonna be pascals, 4272569.58864 pascals. And to convert it to gonna get easier, I converted it into atmospheres, and it's gonna be 42.167 atmospheres. So coming to the second part of the first question. So how does this pressure change if it is considered as a van der Waals gas? So as we got from the question, the A is equal 0.205 atmospheres decimeters in power of 6 per mole squared. And B is equal 1.67 multiplied by 10 to minus 2 decimeters cubed per mole. So the equation of van der Waals gas is equal P equal nRT divided by V minus NB minus A multiplied by N divided by V squared. So what we have now from our previous question, we're just plugging everything in. We're getting this when we plugged everything in. And we're getting, and when we calculate it in our calculators, we must have this answer. P is equal 4.17242. So coming to the next question, number 2. So the 40 grams of helium gas is then added to the neon gas in the flexible container without changing temperature or pressure. This is an important part. This is without changing temperature or pressure. Assuming ideal gas behavior for both gases, calculate the vapor pressure of helium in the system. So here is neon gas, as you want to see. The partial pressure of helium is equal. So basically, what we need to start from, we need molar mass of helium that we can get from periodic table is equal 4.003 grams per moles. So after that, the moles of the neon gas is 40 grams that we get in from our question, divided by 4.003 is equal 10 moles. So what's going on next? 10 moles plus the moles of neon gas is 12.6369 that we will get from the first part of our question, and is equal 22.6369. So 10 moles of helium gas were divided by the sum of moles of helium gas and neon gas, and is equal to 0.4417 moles. So 0.4417 multiplied by 42.167. This is the atmospheres that we got also from the question number 1, and is equal 18.62 atmospheres. So coming to the next question, as you can see nicely helium and neon gas here in the picture. So for the system, sketch Maxwell Boltzmann distribution for each of helium and neon and determine the root mean square speed of each. So the root square speed of gas, we need to calculate it is square root 3RT divided by molar mass, where molar mass gonna be kilograms per mole. So everything, all values that we're gonna get from the periodic table are from grams per moles, and we need to divide them by 1000 to get kilograms per moles. R is the constant value that is equal 8.314. And the temperature we're getting from our first bait that is equal 122 kelvins. So basically all values that we get, we need to plug everything into this equation. So for the neon gas, we're plugging it in, and molar mass for the neon gas in kilograms per moles is equal to 0.0202. And URMS gonna equal to 3088.183 meters per second. So now we're doing everything the same for the helium gas, but the molar mass of the helium gas is gonna be 0.004 kilograms per mole. So URMS is equal for helium gas 472.1989 meters per second. So as in the question, they're asking us to draw the Maxwell-Boltzmann molecule speed distribution. Here you are. Please ignore the purple and the light green because we don't need it for now, and we don't need it in the question. So basically, as we calculated URMS, the value of them is going to be here, as you can see on the picture of the dots. So the neon gas is the yellow one, so it's going to be more closer to 0, the speed of this, while the helium gas, the speed of it is bigger, so it's like more spreaded. So you can see the peaks of them, they're quite different, as you can see on the picture. And here are some references. So please, if you have any questions, you can email me or send or come to me and ask if you have any of them. So thank you very much for your attention. I hope you will have a lovely evening or a lovely day, and I'm going to see you soon. Thank you so much.